Dear students, welcome to today's session on correlation and regression. The objective is to acquire a clear conceptualization and understanding of the statistical tests and their applications. We will discuss about correlation, Pearson's correlation, Spearman rank correlation, regression, multiple linear regression, and potential errors in correlation and regression. Correlation and regression are statistical methods that are commonly used in the research literature to compare two or more variables. Although frequently confused, they are quite different. Correlation measures the association between two variables and quantitates the strength of their relationship. Correlation evaluates only the existing data. Regression uses the existing data to define a mathematical equation which can be used to predict the value of one variable based on the value of one or more other variables and can therefore be used to extrapolate between the existing data. The regression equation can therefore be used to predict the outcome of observation not previously seen or tested. Correlation. Let's discuss about correlation in detail. Correlation is often used as a descriptive tool in non-experimental research. We say that two measures are correlated if they have something in common. The intensity of the correlation is expressed by a number called the coefficient of correlation, which is almost always denoted by the letter small r. Although usually called the Pearson coefficient of correlation, it was first introduced by Galton and later formalized by Carl Pearson and then by Fisher. Correlation provides a numerical measure of the linear or straight line relationship between two continuous variables x and y. The resulting correlation coefficient or R value is more formally known as the Pearson product moment correlation coefficient after the mathematician who first described x is known as the independent or explanatory variable, while y is known as the dependent or response variable. A significant advantage of the correlation coefficient is that it does not depend on the units of x and y and can therefore be used to compare any two variables regardless of their units. An essential first step in calculating a correlation coefficient is to plot the observations in a scattergram or scatter plot to visually evaluate the data for a potential relationship or the presence of outlying values. It is frequently possible to visualize a smooth curve through the data and thereby identify the type of relationship present. The independent variable is usually plotted on the x-axis while the dependent variable is plotted on the y-axis. A perfect correlation between x and y is depicted in the figure 8.1, has an R value of 1. As x changes, y increases by the same amount as x, and we would conclude that x is responsible for 100% of the change in y. If x and y are not related at all, the R value is 0, and we would conclude that x is responsible for none of the change in y. If the data points assumes an oval pattern, the R value is somewhere between 0 and 1, and a moderate relationship is said to exist. A positive correlation occurs when the dependent variable increases as the independent variable increases. A negative correlation occurs when the dependent variable increases as the independent variable decreases, or vice versa. If a scattergram of the data is not visualized before the R value is calculated, a significant but non-linear correlation may be missed because correlation evaluates the linear relationship between two variables. Data which assume a non-linear or curved association will have a falsely low R value and are better evaluated using a non-linear correlation method. Perfect correlations, that is, R value as 1 or minus 1 are rare. Further, the presence of a correlation between two variables does not necessarily mean that a change in one variable necessarily causes the change in the other variable. Correlation does not necessarily imply causation. The square of the R value, known as the coefficient of determination or R squared, describes the proportion of change in the dependent variable y, which is said to be explained by a change in the independent variable x. If two variables have an R value of 0.40, for example, the coefficient of determination is 0.16, and we state that only 16% of the change in y can be explained by a change in x. The larger the correlation coefficient, the larger the coefficient of determination, and the more influence changes in the independent variable have on the dependent variable. The calculation of the correlation coefficient is mathematically complex, but readily performed by most computer statistics programs. Correlation utilizes the t-distribution to test the null hypothesis that there is no relationship between the two variables, that is, R is equal to 0. As with any t-test, correlation assumes that the two variables are normally distributed. If one or both of the variables is skewed in one direction or another, the resulting correlation coefficient may not be representative of the data. The result of the t-test will be invalid. The scattergram of the data does not assume some form of elliptical pattern. One or both of the variables is probably skewed. You can look into the figure 8.1e. The problem of non-normally distributed variables can be overcome by either transforming the data to a normal distribution or using a non-parametric method to calculate the correlation on the ranks of the data. As with other statistical methods such as mean and standard deviation, the presence of a single outlying value can markedly influence the resulting R value, making it appear artificially high. This can lead to erroneous conclusions and emphasizes the importance of viewing a scattergram of the raw data before calculating the correlation coefficient. Let us discuss about the correlation for non-normally distributed data. As discussed above, situations arise in which we wish to perform a correlation, but one or both the variables is non-normally distributed or there are outlying observations. We can transform the data to a normal distribution using a logarithmic transformation, but the correlation we then calculate will actually be the correlation between the logarithms of the observation and not that of the observations themselves. Any conclusions we then make will be based on the transformed data and not on the original data. Another method is to perform the correlation on the ranks of the data using Kendall's or Spearman's rank correlation. Both are non-parametric methods in which the data is first ordered from smallest to largest and then ranked. The correlation coefficient is then calculated using the ranks. Rank correlation can also be used in the situation where one wishes to compare ordinal or discrete variables such as disease versus no disease or a cardiac output. These rank correlation methods are readily available on most computer statistics package. The traditional Pearson correlation coefficient is a stronger statistical test, however, and should be used if the data is normally distributed. Let us discuss in detail about Pearson correlation. A correlation is a number between -1 and +1 that measures the degree of association between two variables which we call x and y. A positive value for the correlation implies a positive association, and a negative value for the correlation implies a negative or inverse association. The formula for Pearson's correlation. Suppose we have two variables x and y, which means x bar and y bar respectively, and standard deviations Sx and Sy respectively. The correlation is computed as below. R is equal to sigma I minus 1 to the power of n into xi minus x bar into yi minus y bar divided by n minus 1 into Sx into Sy. There are some shortcuts, but in general the formula is tedious, and we will let the computer do all this work. Positive correlation. Suppose that an x value was above average and that the associated y value was also above average, then the product xi minus x bar into yi minus y bar would be the product of two positive numbers, which would be positive. If the x value and y value were both below the average, then the product above would be of two negative numbers, which would also be positive. Therefore, a positive correlation is evidence of a general tendency that large values of x are associated with large values of y and small values of x are associated with small values of y. Negative correlation. Suppose that an x value was above average and that the associated y value was instead below the average, then the product xi minus x bar into yi minus y bar would be the product of a positive and a negative number, which would make the product negative. If the x value was below the average and y value was above the average, then the product would also be negative. Therefore, a negative correlation is evidence of a general tendency that large values of x are associated with small values of y and small values of x are associated with large values of y. Here is an example. Let's compute a correlation coefficient between the 1-minute Apgar scores, that is x, and the 5-minute Apgar scores, that is y. And here is a table showing some of the intermediate calculations. X scores are written, y scores are there. The xi minus x bar into yi minus y bar is calculated here. That is, for example, the first value 3 minus 7.9 into 3 minus 8.8 is equal to minus 4.9 into minus 5.8. The value is 28.42. The x bar is 7.9, that is the mean is 7.9, and Sx is 1.75, and y bar is 8.7, and Sy is 1.99. Substituting in the formula, we get a value of R is equal to 0.66. Let's interpret the correlation coefficient. The correlation coefficient measures the strength of a linear relationship between two variables. The correlation coefficient is always between -1 and +1. The closer the correlation is to +1 or -1, the closer to a perfect linear relationship. Here is how I tend to interpret the correlations. -1 to -0.7 is a strong negative association. -0.7 to -0.3 is a weak negative association. -0.3 to +0.3 is little or no association. the values plus 0.3 to plus 0.7 is a weak positive association. Plus 0.7 to plus 1 is a strong positive association. This rule, of course, is somewhat arbitrary, but for some situations I must move to cutoff values closer to 0, and for other situations I may move to the cutoff values closer to 1. You should be cautious not to overinterpret correlation coefficients. Do not assume that correlation equals causation. Also, be careful about how the data was collected. A narrowly restricted sample could lead to a deflation in the correlation. Let us now discuss in detail about the Spearman rank correlation. Spearman's rank correlation is a technique used to test the direction and strength of the relationship between two variables. In other words, it is a device to show whether any one set of numbers has an effect on another set of numbers. It uses a statistic capital R which falls between -1 and +1. The procedure for using Spearman rank correlation: state the null hypothesis, that is, there is no relationship between the two sets of data. Rank both sets of data from highest to lowest. Make sure to check for tied ranks. Subtract the two sets of ranks to get the difference D. Square the values of D. Add the squared values of D to get sigma D squared. Use the formula R is equal to 1, where n is the number of ranks you have. If the R value is -1, there is a perfect negative correlation. If it falls between -1 and -0.5, there is a strong negative correlation. If it falls between -0.5 and 0, there is a weak negative correlation, and value is 0, there is no correlation. If it falls between 0 and 0.5, there is a weak positive correlation. If it falls between 0.5 and 1, there is a strong positive correlation. If it is 1, there is a perfect positive correlation. If the R value is 0, state that the null hypothesis is accepted. Otherwise, say it is rejected. Spearman's rank correlation coefficient. A correlation can easily be drawn as a scatter graph, but the most precise way to compare several pairs of data is to use the statistical test. This establishes whether the correlation is really significant or if it could have been the result of chance alone. Spearman's rank correlation coefficient is a technique which can be used to summarize the strength and direction of a relationship between two variables. The result will always be between +1 and -1. Method of calculating the coefficient. Create a table from your data. Rank the two data sets. Ranking is achieved by giving the ranking 1 to the biggest number in the column, 2 to the second biggest value, and so on. The smallest value in the column will get the lowest ranking. This should be done for both sets of measurements. Tied scores are given the mean rank. For example, the 3 tied scores of €1 in the example below are ranked 5th in order of price, but occupy 3 positions, that is 5th, 6th and 7th in a ranking hierarchy of 10. The mean rank in this case is calculated as 5 plus 6 plus 7 divided by 3, that is 6. Find the difference in the ranks. This is the difference between the ranks of two values on each row of the table. The rank of the second value, that is price, is subtracted from the rank of the first, that is the distance from the school. Square the differences, that is d squared, to remove negative values and then sum them, that is d squared. Calculate the coefficient r using the formula below. The answer will always be between +1 to -1. When written in a mathematical notation, the Spearman rank formula is like this, that is r is equal to 1 minus 6 sigma d squared divided by n3 minus n. Now put all these values into the formula. Find the value of all the d squared values by adding up the values in the difference squared column. In our example, this is 285.5. Multiplying this by 6 gives 1713. Now, from the bottom line of the equation, the value n is the number of sites at which you took measurements. Substituting these values in n cube minus n, we get 1000 minus 10. We now have the formula r, that is 1 minus 1713 divided by 990, which gives a value for r, that is 1 minus 1.73. The value is minus 0.73. What does this r value of minus 0.73 mean? The closer r is to +1 or -1, the stronger the likely correlation. A perfect positive correlation is +1 and a perfect negative correlation is -1. The r value of minus 0.73 suggests a fairly strong negative relationship. A further technique is now required to test the significance of the relationship. The r value of minus 0.73 must be looked upon the Spearman rank significant table as follows. Work out the degrees of freedom you need to use. This is the number of pairs in your sample minus 2, that is n minus 2. In the example, it is 8. Now, plot your results on the table. If it is below the line marked 5%, then it is possible your result was the product of chance and you must reject the hypothesis. If it is above the 0.1% significance level, then we can be 99.9% confident the correlation has not occurred by chance. If it is above 1% but below 0.1%, you can say that you are 99% confident. If it is above 5% but below 1%, you can say you are 95% confident. That is, statistically, there is a 5% likelihood the result occurred by chance. In the example, the value 0.73 gives a significance level of slightly less than 5%. That means that the probability of the relationship you have found being a chance event is about 5 in 100. You are 95% certain that your hypothesis is correct. The reliability of your sample can be stated in terms of how many researchers completing the same study as yours would obtain the same results. 95 out of 100. The fact two variables correlate cannot prove anything. Only further research can actually prove that one thing affects the other. Data reliability is related to the size of the sample. The more data you collect, the more reliable are your results. We will now discuss about regression. Regression analysis mathematically describes the dependence of the y variable on the x variable and constructs an equation which can be used to predict any value of y for any value of x. It is more specific and provides more information than does correlation. Unlike correlation, however, regression is not scale independent and the derived regression equation depends on the units of each variable involved. As with correlation, regression assumes that each of the variables is normally distributed with equal variance. In addition to deriving the regression equation, regression analysis also draws a line of best fit through the data points of the scattergram. These regression lines may be linear, in which case the relationship between the variables fits a straight line, or non-linear, in which case a polynomial equation is used to describe the relationship. Regression is also known as simple regression, linear regression, or least squares regression. This fits a straight line equation of the following form to the data: y is equal to a plus bx, where y is the dependent variable, x is the single independent variable, a is the y-intercept of the regression line, and b is the slope of the line, also known as the regression coefficient. Once equation has been derived, it can be used to predict the change in y for any change in x. It can therefore be used to extrapolate between the existing data points as well as predict results which have not been previously observed or tested. A t-test is utilized to ascertain whether there is a significant relationship between x and y, as in correlation, by testing whether the regression coefficient b is different from the null hypothesis of 0. If the correlation coefficient r is known, the regression coefficient can be derived as follows. The regression coefficient is equal to r into standard deviation of y divided by standard deviation of x. The regression line is fitted using a method known as least squares, which minimizes the sum of squared vertical distances between the actual and predicted values of y. Along with the regression equation, slope and intercept, regression analysis provides another useful statistic, that is the standard error of the slope. Just as the standard error of the mean is an estimate of how closely the sample mean approximates the population mean, the standard error of the slope is an estimate of how closely the measured slope approximates the true slope. It is a measure of the goodness of fit of the regression line to the data and is calculated using the standard deviation of the residuals. A residual is the vertical distance of each data point from the least squares fitted line. Residuals represents the difference between the observed value of y and that which is predicted by x using the regression equation. If the regression line fits the data well, the residuals will be small. Large residuals may point to the presence of outlying data, which, as in correlation, can significantly affect the validity of the regression equation. The steps in calculating a regression equation are similar to those for calculating a correlation coefficient. First, a scattergram is plotted to determine whether the data assumes a linear or nonlinear pattern. If outliers are present, the need for nonlinear regression, transformation of the data, or non-parametric methods should be considered. Assuming the data are normally distributed, the regression equation is calculated. The residuals are then checked to confirm that the regression line fits the data well. If the residuals are high, the possibility of non-normally distributed data should be reconsidered. When reporting the results of a regression analysis, one should report not only the regression equation, the regression coefficients and their significance levels, but also the standard deviation or variance of each regression coefficient and the variance of the residuals. A common practice is to standardize the regression coefficients by converting them to the standard normal Z distribution. This allows regression coefficients calculated on different scales to be compared with one another such that conclusions can be made independent of the units involved. Confidence bands that are similar to confidence intervals can be calculated and plotted along either side of the regression line to demonstrate the potential variability in the line based on the standard error of the slope. Now, let us have a look at the multiple linear regression. Multiple linear regression is used when there is more than one independent variable to explain changes in the dependent variable. The equation for multiple linear regression takes this form: y is equal to a plus b1 x1 plus b2 x2 and so on, where a is the y-intercept and b1 through bn are the regression coefficients for each of the independent variables x1 through xn. The dependent variable y is thus a weighted average based on the strength of the regression coefficient b of each independent variable x. Once the multiple regression analysis is completed, the regression coefficients can be ordered from smallest to largest to determine which independent variable contributes to most of the changes in y. Potential errors in correlation and regression. Two special situations may result in erroneous correlation or regression results. First, multiple observations on the same subject should not be treated as independent observations. The sample size of the data set will appear to be increased when this is really not the case. Further, the multiple observations will already be correlated to some degree as they arise from the same subject. This results in an artificially increased correlation coefficient. Ideally, a single observation should be obtained from each subject. In studies where repetitive measurements are essential to the study design, equal number of observations should be obtained from each subject to minimize this form of statistical error. Second, the mixing of two different populations of subjects should be avoided. Such grouped observations may appear to be significantly correlated when the separate groups by themselves are not, as in figure 8.4b. This can also result in artificially increased correlation coefficient and erroneous conclusions.